all familiar with atoms. You've got some nucleus with protons and neutrons inside of it, and electrons are outside of that nucleus, and they're either orbiting, or they have some wave pattern, or maybe a probability distribution, depending on what model you're talking about. But that's just the atom. It's made up of those three things. And so if we want to find the total mass of one individual atom, we would just need to take our number of protons times the proton mass and a number of neutrons times our neutron mass, and same thing for the electrons, and add them all up, and we get a total mass. So iron is our 56th element. It also has 26 neutrons. And if we're not talking about an ion, if it's electrically neutral, then it has the same number of electrons as protons. And we find that our mass is 1.3726 times 10 to the negative 25 kilograms. But I Googled what the mass of iron was before I started this video, and Google says that it's 9.2733 times 10 to the negative 26 kilograms. So why are our numbers different? So we can find out what the difference between those two values is real easily. That's just going to be some subtraction. So we'll take our calculated mass, and we'll subtract off the mass that we got from Google, that measured mass, and we'll get 4.45 times 10 to the negative 26 kilograms. And that's the difference between what we measured and what we calculated. And then what we can do is, from Einstein's equivalence, we just figure out how much energy that's associated with, how much energy we're apparently missing. And so that is just going to be m times c squared. And so we end up with 4 times 10 to the negative 9 joules, or about a nanojoule, which isn't really that much until you think about this. This is a single atom that has a discrepancy of about a nanojoule, or 4 nanojoules. But what if we had Avogadro's number worth of atoms? Now we're talking about 2.4 times 10 to the 15th joules, a huge amount of energy. And so there is a giant discrepancy between those two values. And this isn't some kind of measurement error. This is actually a fascinating aspect of the atom itself. So for historical context, we're here in the 1930s. And this is when we started to build up our model of the nucleus. It wasn't until 1932 that James Chadwick found the neutron. So it's fairly recent physics that we're talking about here. And this is the puzzling thing. You've got your nucleus, which is made of protons and neutrons. And the nucleus for most atoms is, 1 times 10 to the negative 15 meters, so pretty small. And so if you've got a big element, you've got to force a lot of those protons and neutrons into that nucleus. But protons are positively charged, and they're going to be sitting in a nucleus with other positively charged things, as well as the neutrons. And we know from electrostatics that a positive near a positive is going to repel. And we also know from electrostatics that as things get closer, the force goes up. It's an inverse square law. If they are half as far apart, the force has increased by 4. So it's going to increase exponentially. This should be a problem then. There needs to be some reason why the protons are able to sit inside that nucleus. In fact, there's got to be some force that is pushing them in towards the nucleus, because even if you think about the electrons around the outside, they have just as much electric charge as the protons in the nucleus, so they should be pulling them out as well. So there is some massive amount of force that's going to be holding this nucleus together. And so we call that the strong force. So there's this new force that we've just discovered, essentially, just by thinking through what the nucleus suggests. Because we've got protons that are sitting so closely together and they want to push apart, but they don't, there has to be some force that's holding them together, and we call that the strong force. But as we get to larger and larger and larger elements, that nucleus gets bigger and bigger and bigger and bigger, and suddenly we have, at that high end of atomic numbers, things that just break apart naturally. It's almost as if once you get to a large enough size, the strong force doesn't work anymore. In fact, that's exactly it. The strong force has a range, and once that nucleus is big enough that it exceeds that range, then we start to have our nucleus break apart, and that's where we get things like radiation. But what actually causes them to break apart? There would have to be some kind of force that's pushing them apart, and it's not as strong as the strong force, otherwise it would always be doing this. And so what do we call that force? The weak force. So the difference between what we calculated and what we measured isn't a mistake. It's an artifact of this strong force. There's some force that's doing work and putting in energy to hold that atom together. And so that difference in energy is what we call the binding energy, or how much energy it takes to hold that nucleus together. And so you can calculate how much binding energy any atom has. All you have to do is take its measured mass and subtract from the calculated mass, and you'll get that binding energy. Maybe you'll have to do a c² multiplication if you're trying to get it into joules or electron volts or something like that. For today, though, let's focus on the weak force. The weak force is what's responsible for radioactivity. And so in 1896, Henry Becquerel found that if you just left a sample of uranium out, you would have some kind of expression on a photographic plate. You would see marks. No different than the X-rays that had been created before by Röntgen earlier in the 1800s. And so both of these things seem to emit some kind of radiation, but uranium just did it naturally, whereas with the X-rays you had to have a whole complicated setup to force the X-rays out. And so anything that spontaneously emitted radiation, they said, was radioactive. And other materials would do this as well, like radium and polonium, and a bunch of other scientists found that this was the result, like the Curies, for instance. And what was finally decided was, because these things do it innately, and there's only certain elements that do, it's the atom itself that is causing that radioactivity. And it was decided that it was some kind of disintegration of the nucleus, that the nucleus is breaking down and having some kind of nuclear decay, which is sending out that radioactivity. And so then in 1898, Rutherford decided to name these different types of radiation. And using discoveries from people like Paul Villard, he decided that there was the alpha particle, the beta particle, and the gamma particle, the first three letters of the Greek alphabet, and those were the different types of radiation released by these radioactive elements. So we've got some kind of radioactive sample which is emitting all three types of radiation, the alpha, the beta, and the gamma. And it goes out into what looks like empty space, but we've got these circles with X's through them, and that should be giving you some kind of flashback to the magnetism unit, because what we're actually doing is sending these out into empty space that has a magnetic field flowing through it. So specifically, this magnetic field is into the screen. And so if you remember from good old QV cross B, that is how we're going to get those circular patterns right here. And the alpha particle and the beta particle must have opposite charge because they curve in opposite directions. In fact, if we have V cross B, the alpha particle curves to the left as you'd expect, or my left at least, and then QV cross B, because it doesn't move to the left, the beta particle must be negative. Whereas the gamma, that just traveled straight through, so it shouldn't have any charge at all. And furthermore, the alpha particle goes a lot further than the beta particle before it begins to turn, so the alpha particle must have more inertia, it must have more mass. And so by sending this radiation into a magnetic field, we've just learned a lot about these particles, that the alpha particle is positive, the beta particle is negative, and the gamma particle doesn't have any charge at all. And the alpha particle is also heavier than the beta particle. And the gamma particle, well, we already know gamma particles are just photons, they're just light, they don't have any mass at all. So we're back with our PhET simulation, and I've got polonium-211 here, which you may not know is a radioactive element. It is eventually going to decay into lead-207, and when it does, it's going to give off a burst of energy, and it's also going to send out an alpha particle, and I was really hoping, there it is, that it would have done it by that point. So as it sits there, it's just going to randomly at some point, see that one happen much more quickly, send out an alpha particle. An alpha particle is really just 2 protons and 2 neutrons, or a helium nucleus if you'd like to think of it that way. But the timing on this seems to be completely random on when it's going to decay. But if we were to look at a bunch of these all at the same time, like if I was to dump all of this entire bucket of polonium in here and click play, we see that they are still, again, random, but there's some time period where we have roughly about 50-50 on how many have decayed and how many have not. So even though this whole thing is random, there's what we call a half-life, which is on average when roughly half of them have decayed. And if I let this run, then we would see that the rest of them would eventually decay sometime later, but it doesn't have to necessarily decay. Because this is all probability, there's a non-zero probability that you could have some of these that just don't do anything. Or I could reset this whole thing and maybe all of them will decay before we even get to that half-life. Or maybe all of them will decay after we get to that half-life. So this is the odd thing about radiation, is that it is just based on probability. All of them occur basically at random, but on average, if you have a high enough number of trials, half of them will decay by the time you get to this number called a half-life. So alpha decay is just when you have some element that's gotten too big for the strong force, and so the portion of it that's outside the range of the strong force is going to break off. And what breaks off is always going to be 2 protons and 2 neutrons bound together as a helium nucleus, or what we call an alpha particle. And that alpha particle is not just going to fall off of the atom, it's going to get kicked out with some amount of kinetic energy. And so we can find out how much kinetic energy it has because it's going to be the mass difference between our reactants and our products. And so I've pulled these values from the internet for radium and radon and alpha particle, another situation that's going to undergo alpha decay. And we can just do the mass of our reactants minus the mass of our products. And so what we'll find is that this has got some non-zero value. If we'd used our actual calculated numbers for these are our measured values, then we would have gotten 0. But we don't, so we can continue on. And this is in AMUs. If we had been in kilograms, we could use Einstein's equation. We could do E equals mc squared to find out how much kinetic energy that alpha particle has, but we're not in those SI units, we're in these relativistic units, so instead we just have to do a conversion. We just have to know that this mass difference in AMUs times 931.5 is going to give us this value in mega electron volts. So that alpha particle that gets kicked out has nearly 5 mega electron volts of energy, and it's all kinetic energy. So I've got a setup here where we're going to have hydrogen-3, and the program already tells us that it's going to turn into helium-3, which should be bizarre because we've got hydrogen-3, which is 1 proton, 2 neutrons, and it's going to become helium-3, which is 2 protons and 1 neutron. So whenever this thing decays, as it did right there, it's as if one of those neutrons has transformed into a proton. And in the process of that transformation, where a neutron becomes a proton, it's emitted 2 particles out. It's emitted this blue one, which is an electron, and this green one, which the program calls an anti-neutrino. And that's a bizarre name for a particle, and we're going to get into all of that stuff in the next video when we start to talk about the standard model. But the bizarre thing that should be coming up is that apparently the neutron is able to transform into a proton, and that electron that's emitted from beta decay is not an orbital electron, it's one from inside the nucleus that's kicked out along with this thing called an anti-neutrino, whatever that is, as part of the process of that transformation. So in the 1930s, when beta decay was really discovered, it was kind of an oddity for Wolfgang Pauli. What he was finding was that you had these electrons that are emitted, and at the time, that was all they had. But using that idea of conservation of energy, there were some times when the electron would come out and have exactly the kinetic energy that you'd expect. You do the mass difference thing just like we did in that previous problem and you'd be good to go. But the electron had a range of different energies that it could have. You could detect it as having all sorts of different energies. And so that was what made Enrico Fermi think that there must be some other particle. And the reason why we couldn't detect that other particle was because it didn't have any electric charge. It was like the gamma particle and just passed right through. It was this tiny particle that didn't have any sort of mass, but could carry some amount of energy and didn't have an electric charge. So that is why they called it a neutrino, because it's a tiny neutral particle. There's no fancy simulation to go with gamma decay. It's really just the emission of photons. The only difference is it's not the same emission of photons that we were talking about before with like an electron moving through orbital shells. It's a photon that's emitted from the nucleus itself because these are all nuclear decay products. And the way that happens is the nucleus itself can have an excited state just like the electrons do. And as it falls down from that excited state, then it can emit photons just like the process with the orbital shells, just at higher energy. And so we could talk about half-life for all these nuclear processes, and there is math that goes with it, but I think that we've got enough on our plates right now already that we don't have to worry about it. The formulas look a little bit complicated. You've got this e to the negative lambda t, where lambda is your decay constant, but really what's important to pull out of this is that this is a random process, and on average, half of your sample is going to decay after some time period we call the half-life. And that half-life is determined by this thing called the decay constant, and every material has their own unique decay constant. So we could find out what something's half-life is based off of that property we call the decay constant. So what we've been talking about so far are these spontaneous transmutations, like alpha decay and beta decay is when one element transforms from one to another just spontaneously. But a nuclear reaction is an event when a nucleus is actually struck by some other particle that causes that change. And there's 2 varieties for those reactions. You can have the endothermic reaction, where you've had something come in and put in energy in that collision. And you can have the exothermic reaction, where as part of that reaction, energy is given off. So endothermic is when you have to take in energy, and exothermic is when you give off energy. And for those two types of reactions, whether they're energy releasing or energy receiving, you find this thing called the Q value, which is sometimes called your reaction energy. And there's two ways to find it depending on the information that you have. You could do the initial mass minus your final mass times c squared, and that would give you your Q value. Or you could do your initial kinetic energy minus your final kinetic energy. And either way, the difference in that energy or the difference in that mass, because really they're the same thing, is what gives you that Q value, or how much energy it would require or how much energy it would give off. So this is how you get things like nuclear fission, which is the division of a nucleus into smaller nuclei. And so you can see here you've got a depiction of the liquid drop model, where you've got some sample of uranium-235 that's hit by a neutron. It gets into this excited state. It expands. Once it expands, it has to break apart. And as it does that, it emits more neutrons, which can continue that process. And this is how you have some kind of decay chain, where you can continue that decay, because each time you decay, you send out more neutrons. This is the premise behind things like the atomic bomb and why it's so dangerous, because this can get out of hand really quickly. And if each one of these little explosions produces some energy, and you have a mole or 10 moles or 100 moles of these things going on, you have a lot of energy that is being released. The flip side of that is something like nuclear fusion, where you have things combining together to produce some kind of energy. And that's like what goes on inside of the sun. And so if you were to go through the math and figure out how the sun combines things together to create some kind of energy, you can see that it produces a ridiculous amount of energy. I think I've quoted in here 26.7 mega electron volts per reaction. And then in total, the amount of energy that the sun is producing through nuclear fusion is ridiculous. But as you can tell, I'm accelerating through this content because I think it's important. I would read through these notes, but it's all extra information. As long as you can find mass differences to find things like binding energy or those Q values, then you're good to go. But I think what is more interesting is to delve into things like those neutrinos again. That's a weird thing that we haven't encountered before, and that is going to bring us into the Standard Model. The Standard Model is essentially physics' answer to the periodic table. There are a bunch of different particles that exist in our world, in the same way that there are a bunch of different elements that exist in our world, and we need a way to structure them in a nice, organized way. And that is going to be the content for our next two videos. So, I'll see you on Tuesday.